Hi, it's Ms. Hochstetter to teach you how to do the focus, velocity, and a wave for special cases. So when I say special cases, what I mean is we're going to be using some constants from the reference table, things for like sound or the speed of light, because light is also a wave. So we're going to be using some other constants that we haven't yet so far. So I'm going to show you how to do this. So it says if a wave in a vacuum has a wavelength of 668 nanometers, what color is it? Okay, so first upon reading that, you find that there's really only one number that we know, which is wavelength, and it's also given in nanometers. So we're going to have to think about that when we use that, and we want to know color. So we haven't had a lesson yet on the electromagnetic spectrum, but I'm going to show you where it is in the reference table. So if we scroll down here, the reference table, page 2, there's this electromagnetic spectrum. And electromagnetic is basically a fancy word for light. And there's different things. If you took Earth Science, you've probably seen a very similar table. But these are all light waves. So there's gamma rays, X-rays, ultraviolet, and then here is the visible light spectrum. And you can see between these numbers the different colors that it falls into. And what you'll notice is it says here is frequency. So if we can find the frequency, then we can look here and see where that frequency falls, and then that will tell us the color. So that's how we're going to use this. So we need to find a frequency to solve for the color, but there's something else we need to do. We need to find an equation that relates frequency and wavelength, and maybe another variable that we need to know. So on page 5 in the reference table, these are the equations. I'm just going to go ahead and show you. We're going to be using the velocity equation, frequency and wavelength, but then we need this velocity. So this is a light wave. So we need to know the speed of light. And so if you go to the physical list of physical constants on the first page of the reference table, we're going to come down and there we go. Speed of light in a vacuum is this number here, 3.00 times 10 to the 8th meters per second. So it's a very big number. It's a very fast velocity because light travels very fast. Okay, so now that we have that information and we know our equation, we can set it up to solve. So I'm going to do 3 times 10 to the 8th meters per second equals frequency times 668 nanometers. Okay, let's address those nanometers. So nano, we need to convert it into meters, but we need to know how much nano equals. So what we do again is we're going to go look at the table, constants, prefixes, powers of 10. We're going to look here, and we're going to look for something that has an N for the symbol, because it was said symbol. So you might not even know that it actually, the word is nano, but you can look at the N here, and then that tells you it's nano, and we see that it is 10 to the negative 9. So it's a very, very small measurement, which again makes sense because it's a light wave. So I'm just going to rewrite this. So 3 times 10 to the 8th meters per second equals frequency times 668 times 10 to the negative 9 meters. So all that I did here is I took this, I looked up the value in the reference table, and then I substituted it with the actual value. And now I am good to go. So I can just solve for f. So I'm going to divide by 668 times 10 to the negative 9 meters. That cancels out. I'm going to divide that over here. And when we do that, we are going to get a very large number. So let me just pull that up. Okay, so once we do that with the calculator, and you might want to put parentheses around when you divide, because if you don't, it'll mess up the exponents and you'll get a different number. But when I do this, I get 4.49 times 10 to the 14 hertz. So that's not the answer to the question because it's asking for color, but at least now we have a frequency and we can look it up. So 4.49, we're going to go down here. So like I said, it was 4.49 times 10 to the 14 hertz. So we see here all of these end in 14, 10 to the 14, so that's good. That means that we hit the visible light spectrum. So 4.49 is actually going to fall right in between here, 4.49. And that means the color is red. So the answer for this is just red. Now, sometimes with this focus, instead of giving you a wavelength, I might just actually give you the frequency. I might say, find the color, if a wave is in a vacuum and it has a frequency of blah, 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 what color is it? And what's nice about that is it basically cuts out all this stuff here, but it just depends because, I write the focuses so that they switch what it's asking for. So I did the hardest example here so that if you, again, encounter wavelength, you know how to do it. But if it gives you frequency, what's nice about that is you can just hop down here and look at the table and solve for it. Okay, let's do the second one. So what is the wavelength of a 15,662 hertz sound wave in air at STP? Okay, so again, we know a wavelength, 156. No, we don't know the wavelength. That's what we want to know. We know the frequency is 15,662 hertz, and we want to know wavelength. So again, these special cases, the speed of sound in air at STP is actually a constant. So we need to look up the sound wave speed at STP. And STP just stands for standard temperature and pressure. Because, if it's warmer out or colder out, that's going to affect how sound travels. But for the purposes of this, we're going to assume that it's speed of sound at STP. So we look in our table of constants and we see speed of sound in air at STP is 3.31 times 10 to the second meters per second. So that is the value we are going to use, 3.31 times 10 to the second meters per second. So we set that up, V equals frequency times wavelength. 331 meters per second equals frequency 15662 hertz times my wavelength. And then when I do that math, I'm going to get an answer of the wavelength is 0.0211 meters. And it doesn't say it on here, but I'm going to go ahead and round it to the hundredths, 0.02 meters, because that's what it's going to ask you to do on the Google form. Okay, so that's how we do that. And again, this one might change too, like it gave us the frequency, but maybe sometimes it'll give us the wavelength, and then you'll have to solve for the opposite and vice versa, but at least now you've seen it done one of the ways. All right, that's it for now.